Hello, everyone. Today we'll be talking about integrating hydrometeorological data analysis and sewer hydraulic modeling for assets/utility management. We'll be taking a look at two case studies. I'm Henry Boateng, staff professional and hydraulic modeler with Withers Ravenel, and my master's at Texas Tech in civil engineering, primarily in water resources.
And I'm Alin Akli. I'm also hydraulic modeler at Withers Ravenel. We are basically serving a lot of small cities and municipalities across and within the North Carolina borders.
So today we'll be looking at America's water infrastructure. So one problem with, being an industrial giant or being able to industrialize that early is you would have aging infrastructure. So as of now, there are water lines or sewer lines that are made from clay or are made from wood. And all of these old infrastructure is fighting against new age problems, new age RDI problems, new high intensity rainfalls. So we cannot go back to the old, traditional way of modeling where it was more focused on let's get the information, let's build, a skeletonized model, or in some sense, a calibrated model. But we should move more towards a data-informed modeling where we can be able to incorporate things like, the usual flow monitoring data, assessing past events to see how it affects our system going forward, and also involving hydrometeorological information. So rainfall in particular, because we may debate, climate change as a phenomenon. However, the climate is different from what it is, today as compared to what it was, a few years ago. As an engineer, when we build our models, what's the next thing that we do? Most of the times you'd realize that these models will end up being on a shelf or does not really influence developmental, decisions. So today we'll be taking a look at two case examples where our model can be able to influence, some of these decisions and also dig more into how hydrometeorological stuff influence our model. So our first case study is Gastonia. That's a basin in North Carolina. So where we will be primarily looking at is the Firestone Basin. I know many of you all may be thinking that why are the pictures so thrown in there? It is to serve a theatric effect. So this confusion, if I may put it that way, is a reflection of the sewer systems in the US. So because it's so old, there are certain portions in the sewer system where, you may have a house sitting on a sewer line or, information has not been collected to the point where we do not exactly know what stops what. Or, for example, water lines, if I shut this, the water isn't going to stop. Some may be shutting a valve and water is not stopping. So being able to, know all of those things that are underneath where we are standing is something that many cities grapple with. So this is to give you an idea as to how our sewer systems, we need to focus more on figuring out what's exactly, down there. So for our fire basin that we looked at, it had 42 miles of gravity sewer, almost 1,000 manholes, and there were 22 flow meters that were shuffled around depending on the time of the year. So although we have our outfall somewhere here, we also considered the downstream of our outfall. What happens if we are to go with a particular alternative? What is going to happen downstream? How are the people going to, be affected by a particular design alternative that we go with? So as usual, the scope of this analysis was pretty simple. The normal, flow meter network assessment and creating a representative hydraulic model, checking the recent impact of numerous projects that have been done. And that is one important thing that most of the times it tends to be overlooked. So we sometimes may be focused on, oh, let's fix this. Let's put in this new line. Let's do this rehab. Are we actually checking to see how these numerous projects is it positively affecting our system? Are we actually solving the problems that it was designed to do? Because a lot of the times there are no checks and balances after, we do this project. And we would also take a look at, a design alternative to solve some of these problems that the city is facing. So as I said, previous projects have been run, SLRAD, CCTV, flow metering, data mapping, and even weather analysis. So work has been done in this particular basin to try to solve, the hydraulic that they've been experiencing. So with all of these numerous works, and these are the ones that are put in. There are other ones like running a parallel line, and also even doing something called a private line disconnect, where the city goes around to check if there are any maybe some pumps that are connected to the sanitary sewer that is not supposed to connect. So with that one, you can be able to kind of see from the effect of the hydrograph. So you may have a hydrograph, go up, peak, then as it's coming down with no rainfall, you see a sudden spike. And that is to tell you that, okay, there might be a sump pump in your system. So Estonia as a city is very big on data collection. So for our model, these are the different flow meters that we use. They are currently color-coded based on how useful the data was, the quality, and even the time duration that it was in. So as modelers, when we are done with our whole system, what we do is we check to see, okay, I built my model, it's calibrated and everything. I'll run design storms through them. And, design storms is the maximum precipitation between a set interval. So for our period, 2-year, 5-year has its own, corresponding design storms. So what we did is we took a look at the rainfall information for the past 6 years. So up to 2021. And that's half of 2021, not the full. And we realized that these, design storms that are said to happen 2 years and 5 years. For example, if you take a look at 2018, 5-year storms happen about 3 times. And it's not supposed to happen that frequently. It's supposed to be, every 5 years. So then it throws a question to you. Do we have to strictly stick to, our design storms as a measure of our system's, function? Because those IDF curves that were created years ago were in different climates. And now the climate is absolutely different from what it was before. So that is a question that I threw to all modelers, that when you are building these models, try to, in some sense, verify your model with past information and not just stick to, these design storms as a means to, kind of verify your model or to check to see your model will be able to withstand. And if you are just sticking to these things, be sure that you are also considering all the future scenarios to make sure that whatever it's taking now, you can be able to, handle it in the future. So for example, if you take a look at this rainfall graph, it's on a positive trend. So as we go across the years, the number of high intensity rainfall increases. So that is, a question that I hope you all think about and see the next way forward. As I said earlier, historical analysis. So for our historical analysis, we did all of these analysis in R. So all of these graphs were made in R. A quick look at this one, you'll be able to see that this gray line represents the diameter of the pipe. You can see that the flow, the depth of flow in 2019 as compared to 2022 has reduced almost 50%. So it was around 12 here, and now it's around 7.5. So that is a reflection of the work that's been done. And that goes into us looking at how are we bettering our system? So how are these projects that have been done previously, is it really positively impacting my system? Being able to go back and take a look is very, very important, because if you do not know where you're coming from, you definitely will not figure out where you're going to. And it's the same, kind of the same graph here. However, this is in terms of the percentage of rainfall entering the system. So in 2019, for the same flow meter, it was around 0.2, and now it's around 0.1. So that's also almost a 50% reduction in flow. So after we are done with our calibrated models and everything, and we looked at our values, it was around 2 to 16.5. So the idea is, it's around 16.5. Let's do rehab, or let's take out that line, and there might be some infiltration, but there is the law of diminishing returns. What point are you going to stop? At what point are your renewal efforts, your R&I renewal efforts, at what point are they not going to make a big impact in stopping all of these hydraulic issues that your system is experiencing? So for 16.5, as compared to all the systems that we have modeled, 16.5, that is pretty good, at least in terms of rainfall percentage that's entering into a system. So for this, we realize that it is not the hydraulic issue is not a function of RDI necessarily, but it's more of a system issue, where the slope here in this area is really low, and the pipes there cannot be able to take the flow. So it is better, instead of just doing rehab, it is better for us to reroute the flow from the existing area from here to the R4. So this was the alternative. So we rerouted the flow from here to the R4, and this solved all of the issues. So rather than just moving straight to rehab or just doing lots of CCTV, figure out if actually a structural issue where the capacity of the pipes there will not be able to withstand the flow that's coming, and it's not really a function of RDII. So when we run the model for the alternative, so that is before, and all of these red dots signify hydraulic issues that the system was experiencing, at least for a 10-year storm. And then this is what happens when the alternative has been implemented. So this proves to show that this particular alternative is helpful, rather than just trying to rehab this whole line, which will cost more money with easements and everything, since it's so close.
Okay, thank you, Henry. So the other story is also for a small city located in North Carolina, and I have to go over that story a little bit fast given the limited remaining time. So the city of Goldsboro sanitary sewer system received wastewater from 34,000 people, and also Seymour Johnson Air Force Base. It has 230 miles of gravity sewer, 26 lift stations, 18 miles of force mains, and all of the wastewater is conveyed to a wastewater treatment plant. So I put this map here to show you that, the major interceptors all of the large lift stations and wastewater treatment plant are located in FEMA 100 floodplain zone. Next, please. So the hydraulic characterization was part of asset and inventory assessment, with the ultimate goal of helping the city to be more proactive and viable in managing their wastewater asset. All of the red dots that you see in the maps, so basically showing the conditions, poor conditions of the system, as we scored using all of the data, for example, CCTV and other data that we had. And also I already showed the FEMA map. 1/3 of the system is located within the critical infrastructure and natural water. So knowing all of this information, next slide, please, Henry. I'm gonna yeah. So we started collecting the data last year from mid-September. Mid-spring to mid-summer. For this short period of time. So as a modeler, we always prefer at least having a year-round data to be able to capture all of the seasonal and monthly variation. But the project budget and schedule is not always defined by us. So we had a 3 months limited data of last year during the summer, basically. And what we observed is a consistent decline in wastewater flow during that monitoring period. We have access to USGS data of Neuse River, which is very close to the city, and also groundwater level. And for both of them, we saw the same trend. Both of them decreases over time. And all of these data indicated one thing: hydrologic context impact hydraulic characterization. So knowing this fact, the first thing that we have to look at the historical data. And what you see here in this slide is the average, monthly average of the last 12 years of the data for the groundwater and also the Neuse River depths. The trend is expected. We have higher levels at the winter and lows at the summer. But what is important here is the range. The range can vary significantly. And as a consequence, the flow in wastewater system can vary significantly during the year. So this is the same data plotted in different ways. And what you see here is the basic correlation between river and the groundwater level. And also it's kind of it's a logarithmic trend. For simplicity, we define two main regimes: one low groundwater and one high groundwater levels. The low groundwater level, basically, they are not correlated. A high groundwater level, we have a positive correlation to each other. So 2022 data was located in low groundwater, while we have high groundwater data from 2016. And using the combination of these two data, we estimated the dry weather groundwater infiltration. And as you can see this graph, it varies significantly from 3 to 8 mgd, depending on the groundwater level. Since the wastewater treatment plant capacity is 14 mgd, during high groundwater level, more than half of the incoming wastewater could be only groundwater infiltration. Same trend was observed for the wet weather also. We had higher RDII response and also higher deviation in RDII response when we had higher groundwater level. So basically, this schematic shows whatever I already explained to you. For the same system, same base sanitary flow, if for different hydrologic conditions under the same rain events, we will have different flows because groundwater infiltration and RDII are really different. So using all of this information, we try to evaluate the system performance under 10 years design storms. What you see here is basically what red means danger, hydraulic constraint, orange means kind of alert, close to hydraulic constraint, and the greens are okay, good to go. So what we see is basically for the high groundwater, we know, we already know that what rehabilitation and improvement has been done during the last 6 years, and we take that information into consideration for estimating the dry weather flow and RTK parameters. So knowing all of these, next slide, Henry, please. So this is the same information showing in a more quantitative ways. We see that total volume, basically system response to the rain can significantly vary. And if we only use the 2022 data, we basically underestimate hydraulic constraint. And any planning and decisions made based on that was improper and inappropriate. So basically that's it. And the only take-home message from this presentation is that no matter what the information that we have, what the data that we have, try to extract as much as information that you can, which is critical for better informed decisions and system operation and planning. Thank you very much.